누구 어느 분 말씀하시는? give you some example about the science and application of the solar module science in terms of the measurement from space or how the space acceleration can be useful. And then I'll give you some overview about the technology that's available for space-borne remote sensing. And that's what we talk. And what we talk about space-borne remote sensing is sending people on the ground to make the measurement is very challenging, particularly for many challenging terrain and complex areas. And remote is the only way that can reach those regions all the time and anytime that we like. And then I'll give you some highlight about the future, and then I'll give you some rating. So why so much is so important? In fact, the amount of water in the soil, in fact, is not that much. Most water on Earth is located in the ocean. But actually, this even tiny fraction of the water in the soil is so critical because it's a connection between what we call the water, energy, and the carbon cycle on Earth. Because the availability of the water, right, affect the energy exchange between land and hemispheres through the evaporation and so on. And then the availability of water, right, allow the growth of the vegetation. It's a connection of all three different cycles. So therefore, it has many important science and application. And then from the application point of view, I think we're all concerning about the future, right? The climate change, more shorter term with the change of weather condition, and then and more natural heritage, right? The flooding, and then the drought, right? That's also coming up, and maybe impacting feeding people on Earth. And there are three major types of technology. One type of technology, what we call radiometry. Radiometry measures the emission of any natural object. In fact, anybody, including the human body, will radiate of frequency, what we call about the 1.4 gigahertz frequency, very close to the cell phone frequency that we use. So we all radiate. And so the amount of water in the soil actually affects the amount of radiation, the amplitude of radiation from Earth. So by measuring the intensity of radiation using this kind of radiometry, we can infer the solar motion information. And another different type of technology is called radar. So radar is a pulse, and I see everybody is familiar with the radar, right? Radar sends a pulse, then the echo that come back. In fact, also depends on the amplitude of the solar motion. And then the solar motion will affect the reflectivity of the soil. So the more soil water available, the reflectivity gets stronger. So radar signal, in fact, can also allow us to the information of the solar motion. And the newer technology is called bistatic radar. So the receiver and transmitter are not coordinated at the same location. And so one will transmit, and then whatever signal that's available from space, then we just need to deploy a receiver to detect the signal. Again, it's the same thing, just like a normal radar. The more water available, the stronger the refraction is going to be. The primary difference between those three technologies is the spectral resolution. The synthetic aperture radar has a highest resolution, the 10-meter resolution. So that's why a lot of people are highly interested in that. But the radiometry has the most precise observation in comparison to the technology. So we need to take account of all the technologies that are available in the future, because they all complement each other. Let me use the observation from NASA solar motion active and passive mission to provide some example about how the solar motion can be used for many applications. And the SMART mission was launched in 2015, about 10 years ago. So it has been acquiring data for 10 years. The primary instrument on that is so let me focus on the application of the data from the satellite. And this is the animation that shows the change of solar motion pattern in the Southern California, with the western part of the U.S. In the early part of the year when there was a rainfall happening all the time. And we can see whenever there's a big system come over, the solar motion will change accordingly. And then if we focus And so in the past few years, our JET has been also actively working with the domestic United States Department of Agriculture Service to put the data into the user's hand, domestic within the United States. Now the Western office proportion that also has been adopting the SMED data for the policy monitoring. And so now let me switch gear, focus on more than just the crop education. And so again, we close the work. And so this provide information about the likelihood of the flooding. And so the hypothesis of the precondition, the priori assumption is when the soil has been wet to start with before significant rainfall, then it's more likely to lead to a flooding. And indeed, that's the case. Based on the analysis of the soil moisture condition at present time, and then according to the precipitation rainfall that may be coming over, then indeed the river discharge information reflect the condition of the both. So the positive portion is very strong. So meaning that the knowledge of soil moisture information in fact is very crucial and allowing us to predict the flooding probability positively. And as member radiometry in fact also provide additional information, not just the soil moisture, but also the amount of water contained in the vegetation. So now you can probably imagine once you have the information of soil moisture, and also vegetation water content information, that information in fact is pretty important for the prediction of the wildfire, right? And so the more dry vegetation mass available, the more likely the wildfire may happen. So they have analyzed, so a group of researchers in the US analyzed about 500 wildfire events. So what they have found is pretty close what you can naturally can predict. When there was a strong rainfall, right? Maybe a few months before there's the wildfire event. And then once the rainfall happened and then a lot of moisture become available, then the vegetation will grow. But if the drought, right, happen afterwards, then the vegetation will dry down, and then a lot of dry mass become available. If after the temperature, right, become pretty bad, and then therefore the dry soil moisture condition together with a lot of biomass, and then it can lead to the wildfire condition likely. And so we have I have touched on the example about what you can learn from the coarse resolution radiometry data. But we are very interested, a lot of people are very interested in higher resolution data. So a new mission coming up called NASA ISRO synthetic aperture radar mission has used radar technology that can provide meter spatial resolution. And so you'll be launching this soon, about a few months ago. And so this chart gives you some idea about what you learned. That's not available from the coarse resolution radiometry data. And so the upper image here show you this one corresponds to the coarse resolution radiometry data, and the lower portion corresponds to how the combined radiometry and radar together can provide you with more spatial detail. So spatial detail in fact is very crucial, as you can imagine. Let me switch here. And then this is more detailed and more spatial information to provide you the information about the amount of water the farmer uses to irrigate and in comparison with the coarse resolution radiometry data, so now you can see the importance of the high resolution information in the soil for the irrigation and monitoring. And now let me talk about the mission that has been launched in the past few years. So radiometry. So there has been a long history, and so SEHA remote sensing technology for radiometry started in 1980, and then since then there have been many radiometry launched in space, and so the frequency continued to get lower, and then a few years ago, about 10 years ago, 15 years ago, these are small SMAP has very, very carefully designed and select those locations so we quantify quality of SMAP renal data. And so that's what our trick here is for, to establish a collaboration with your institute. And hopefully can get more systematic management in the Asia region. And so one area that we want to focus on is the forest. Andrea will cover that. Let me skip it over. And the big dot here corresponds to the current location of the south side that we have. And so one feature we recognize is we had almost almost nothing. No cover in Asia. And now we are pretty happy that Dr. Kim is able to set up a very important site in South Korea. And I think which will become a very important asset. But for more than SMAP, but also for many other missions coming up in the coming 20 years. So I'm hoping this site can become a step for many scientific executives to look into. Let me skip this chart. I'm just going to take that. And so I got a very cool picture from Dr. Kim. That's a site that we're working, so I will let Dr. Kim talk with that with you sometime in the future. We're also working with some people in Malaysia to set aside in Malaysia. So I also visited Thailand. Thailand, they have shared the same concern with me. How would the drought affect the production of rice paddy, rice production in the country region? So the same common concern that many people here in this region. And so this is the site that we are considering in Thailand. The same concern that has been shared by the people of Vietnam, rice paddy production. On the same thing, they import rice from many different countries, and I think Korea is importing rice, right? And so I think that's a huge issue. Many people in this region need to remove. Okay, in summary, so much is really quick remote sensing parameter that will allow us to have a global look and also the application of many things that I mentioned earlier, flooding, wildlife production. And there's three key type of technology, and all those are okay. And finalize the partnership that we're doing here. I'm hoping it can become very successful, and we can have it. And in fact, many countries and the ESA and NASA agency what we providing to the global community. Okay, let me come to conclusion here. Thank you. We should just continue the presentation, then we can have a Q&A at the end.
Yeah, I think we can do that too. So
Yeah.
please,
Okay, yeah.
as it doesn't matter. So I think, well, once again, thank you, Dr. Yo. I know that this is quite topic to many students, but this is really about a great opportunity for upcoming, for you guys basically. And then, okay, so we'll move on to our next speaker, Dr. Rajat Bindish, and then he will continue on the discussion about this soil motion missions, NASA, and the future collaboration with basically GIST results.
Thank you so much. I'm very glad to be over here working with Kim, who was hosting us and very graciously invited us over for the collaboration. And we are very excited to develop some of the things that Simon mentioned about in future. We hope to come here more frequently and try to address as many questions can that we have on microwave remote sensing of soil moisture or microwave sensing in general. So that Simon mentioned, we're doing, we have launched smart mission, and there are many other missions that will be launched in future. But one question is, how does one measure soil moisture? Like from remote sensing, like why do you use microwave? Why not some other frequency? So I'll try to give you the basics of why we try to use microwave as compared to some other frequency, and then try to do some very broad overview of the retrieval algorithm there may be some overlap on the slides, but I try to walk through those slides quickly. But our slides are overlapping. So we heard earlier that we use microwave remote sensing for soil moisture. But the reason why we do it is because soil moisture, impacts the dielectric constant of the medium. And a microwave that we take, a measure from space, is a function of the dielectric property that it is observing. So that's the reason why we use microwave frequencies for soil moisture. Otherwise, you could think, why not this IR? Why not, X-ray? Why not some other frequency? Because the relationship with the dielectric constant is what allows you to do soil moisture. So this shows you the relationship between dielectric constant and frequency. And for microwave frequencies, you can see that the dielectric constant of water is like all the way to 80%. If you're looking at the frequency, then the dielectric constant essentially is close to zero. You will not be able to do soil moisture using those frequencies. And also, if you look at it for L-band, that's what Simon had mentioned, that for SMAP and NISA, we're using L-band frequencies, which are close to our GPS 4 gigahertz. That dielectric constant is close to 80. So it gives you a big range from 80 to 0, which is 0 is dry soilers. 80, different. That is what allows you to do soil moisture sensing. Next. So this graph shows you the relationship between dielectric constant and soil moisture. As I mentioned, this is the relationship that allows you to retrieve, once you get the dielectric constant, to invert it all the way to soil moisture. So in future, when you be trying to do retrievals and looking at data, this is what you'll be looking at in terms of how do you get to soil moisture finally from NISA or SMAP or in future. That's what governs the relationship between soil moisture and dielectric constant. We also talked about which frequency to use in microwave remote sensing. As Simon mentioned about SIMA, which was much higher frequencies, and in future we have moved more and more closer to the L-band frequencies. And the reason being, for L-band, you have to, for any frequency, you have to look through the vegetation, because when you're looking at paddy, for example, there's a lot of vegetation on top, and you're trying to do soil moisture at the bottom. Can you see through the paddy field? If you are doing very low frequency, then you can. But if you're doing high frequency, then you can't see through the paddy field. For example, when you use a 10 gigahertz, you essentially not much of the soil. Whereas when you're looking at 1.4 gigahertz L-band, it has penetrated through the vegetation that allows you to see the soil underneath, as compared to the shorter wavelengths or higher frequencies that cannot penetrate through the vegetation. So that's very important when you're trying to see which satellite to use for the moisture. You want to use the lowest frequency possible and use that to do soil moisture tables. Otherwise, you'll have higher and error in your tables. I'll quickly go through this, as Simon already talked about this. These are the three different techniques. One is the passive microwave, which is what SMAP uses. And an active microwave, you have a transmitter and a receiver, which is what NISA is. We also have a fluctometry, which is a SWAP, where we have a transmitter over here and a receiver, which is what you use for observing those frequencies. These three technologies, all three of them provide you a means of doing soil moisture. Some of them are more easy to predict, some of them are difficult, and I try to explain to you why some of them are easier and some of them are more difficult. This providing soil moisture in future or currently are providing, which is NISA will be providing it in future. Cygnus is currently providing soil moisture. Aqua, which was follow on is the AMSAT 2 and AMSAT 3, also provides moisture, but it uses C and X band frequencies. So as you saw earlier, those will have typically have higher errors, but the data from C and X band goes all the way back to 1978 as well. So if you really want 50 years of data at C and X band, that type of data is available. And then you also have SMAP, which is something I talked about last in 2015 and currently provided the last 10 years. Besides these, you have a number of international satellites like GWS and SPOS also are available and provide you sensing data. This is another table that I like, which shows you different satellites which provide you soil moisture. I've tried to color code it where the red ones are the ones which are in C and X band, and then the orange one is basically GNSS reflectometry, is the CTIF, and then you have the L-band missions over here, and then you have the reflectometry mission over here, and then you have the NISA over here, which is so the last block over here is the L-band missions, includes radiometry missions, radar missions, and reflectometry missions, all blocked over here, which are all the L-band. Can skip over this, but essentially SPOS launched it for 2009. It has been providing data for the last 15 years. It has a global revisit of every 2 to 3 days. So you have 15 every 2 days using SPOS observations. And a complement to that is the SMAP observed data, which was launched 10 years back, roughly. And data is available at NSIDC and global coverage of every 2 to 3 days. And then you already heard about CIMAP, so let's skip over that. The next thing I wanted to talk about is, you say that you have remote sensing observations, but how do you get to soil moisture? So the remote sensing macro observations are impacted by a number of factors. On top you have the atmosphere, then you have the vegetation canopy, then you have the soil layer. Atmosphere at these long frequencies is almost transparent, so you include the atmosphere. But you have to account for the surface vegetation scatter as well as the soil and the vegetation interaction. So those were the terms that you have to account for, which is these three terms. These three terms, besides these, you also have to account for the roughness factor, this vegetation interaction part, and a relationship that allows you to do the roughness correction. So this presentation, these slides are meant to be an overview, and then if you are interested in doing algorithms, you can certainly go and dig into those papers in detail. And in terms of vegetation, we talked about, we have the effect of vegetation listed over here. So you have low vegetation, you have, when you have low vegetation, you have higher dynamic range. As you vegetation, your dynamic range of soil moisture to wetness temperature decreases. So as you increase the vegetation, your error goes up, or your certainty, the amount of certainty you have in terms of retrieval goes up. So this is the important factor when you try to do retrieval is how much vegetation you have and you have to account for the vegetation. So in terms of the retrieval, you have to worry about three different terms. One is the surface part, and then you have the vegetation part, and then there's vegetation interaction term, and there are equations for each one of those terms. In the end, you can put it all together. What you get is a top additional equation, which you, if you have been looking at retrieval algorithms, you'll be using that a lot, which is the zeroth order top. If you have some vegetation interaction, then you can have a first order equation. This is zeroth order equation. As you saw, this equation has a number of terms. So for solving this equation, either you have to make some assumptions, or you have to put in some X-ray data that allows you to do the retrievals. For example, you need some soil texture that you already know of for most part, and also information about vegetation. Or you can use passive product, then you allows you to constrain the retrievals and do much better accuracy as compared to just an active retrieval. So that's the advantage of doing a passive retrieval. This shows you a basic forward model where you have a surface scatter, which is the first term, and then you have the volume scatter, which is second term, and then you have the double bonds, which is surface to vegetation and back to the satellite, which is the double bonds term. And there are a number of different retrieval algorithms or approaches which are outlined in this. Since the active retrievals are generally more complicated because of the scattering theory involved, as well as the micro observations have to pass through the vegetation twice, once when through the transmitted and one when is reflected back. Whereas in reality, it only has to pass through the vegetation once. So it's much easier retrieval compared to the radar-based retrieval. There have been a number of approaches that include just an empirical approach, or others use neural networks, others use Bayesian approaches, or water cloud model, or physics scattering model. They're all based on how much sensory data you have and what assumptions you're willing to make and what compromises you're willing to make into observing the retrieval. And in some of them we need more sensory data, some of them we need less sensory data. So there are pluses and minuses of each. This shows you an image of the tree when it was ready, close to ready to launch, and this shows you a time series of observations using UVSAR data, which is similar to the NASA data in the future, which was collected over Canada in 2012. And the data, once NASA is launched, will be available through the NASA DAC, as well as SMAP NASA data also will be available through NASA. I quickly want to touch upon this reflectometry retrievals also. So one of the upcoming techniques is reflectometry. This shows you a comparison between kind of radiometry and reflectometry. Radiometry retrievals are much more mature. They have been going on for 40 years and well established. SMAP has been doing retrievals for the last 10 years, has been doing it for the last 15 years, and there are a number of field campaigns that allowed us to use radiometry techniques. Whereas the SOAP or reflectometry techniques are much more new, and there's a lot more physical modeling development still to be done. So that's an opportunity for you guys if you want to be looking at that type of data, how to develop those algorithms in the future for GNSS retrievals valuable. This shows you some of the parameters which are, so it is similar to radar. It has a number of parameters you worry about, and some of the papers that have dealt with the 6 sound-master retrievals are listed over here. You'll notice that the second paper is something that Dr. Kim worked with during his PhD. So you can certainly ask him about his retrieval approach, and he can guide you more about these other retrieval approaches also. With that, I have Andreas, who is going to talk about validation of these products. We can't just have that, but we also want to validate it to see how accurate it is.
Thank you very much. So as we planned, I think we will just continue the presentations, and then Professor Kim already got some of the questions, and he put together PPT. So we will put up the questions, and then we will open the floors for extra. So the next speaker is Dr. Andreas Corianders. He will continue on this discussion about solar moisures and NASA missions. Thank you.
All right, thank you. Happy to be here. I'm going to talk about the validation of this solar motion measurement, and I'm going to talk about them in context of SMAP mission. So I'm going to show you one more graphical representation of SMAP. Here you can see it actually spinning in this animation. You see how it covers the Earth with using this conical pattern. So it receives the radiation, its radiometer receives the radiation from the Earth, and the networks can span continents and you have reference points, but you don't have accurate average on those reputation, but you can use those measurements in other ways. And then you can compare the measurements to other satellite products, model products, and make conclusions about how well you think your product is doing, even though it's not maybe similar kind of quantitative reference as the polarization. And then lastly, field campaigns are measurements where you have a certain type of intensive measurement going on, where you do a lot of measurements and you can solve specific issues by doing these intensive measurements, but it's hard to conduct those over long periods of time or over multiple occasions. So it's sort of focused on certain things. I'm going to talk about the core validations and then field campaigns in these coming slides. So first, so SNAP established this kind of core validation site, which Simon mentioned briefly that we showed that SNAP meets its desired requirement. So we have these stations around the world, and core sites are a subset of all these soil moisture sensors shown on this global map. Partner with different people, investigators running those networks. So SNAP and NASA deploy all these measurements. It was deployed by local investigators, including this kind of research for hydrological purposes or validation purposes, similar as Dr. Kim is doing here. So we have these core validation sites, and then I'm going to show you how their the variability or diversity of these sites. So you see the black dots are the stations, and basically the big red box is my footprint represented on a grid set. And so now I'm going through these different. So you see all this diversity of you have the background is a different type of land cover. We don't need to go to exactly detail what the different colors mean, but you see the land cover in the background changes. You have different layouts of the stations, and it's actually the black box is the radio in the footprint. And so you have them, and you see the location on the right there, all over the world, different of layouts of stations. So this black box is about 30 kilometers by 30 kilometers. So it's a big area because the measures a large footprint, as Simon explained. So we have a lot of them, and we need to take so they have investigators on the ground who are making these measurements, running these stations, and then we take that data and we process it so that we can use it in the validation. So we need to then use those multiple station measurements and average them as a number, and one way of doing that is like do these weighted coronoid diagrams where we can avoid weighting certain stations too much and making sure we estimate that average value as accurately as possible with these different layouts. And so eventually then we'll get to the comparison. So we average those stations, we get reference value, which is the red curve on this plot, and we compare to the retrievals, which has different algorithms, provide different soil moisture measurements in this case. And then we need to do this from all the sites. We do this kind of assessment of how here is the black dots compared, or is the base algorithm producing this map soil moisture, and it's compared to the reference moisture in the red, and the scatter plot we see how it does. So we have different performances of different sites, done by different land cover conditions and other type of situations. Put that all together in a table, we get big scatter between all, we get statistical analysis for different parameters. And in the end, NASA basically wants one number to show that we are successful. So this is from after all this processing, so this is the number. So, and if this number is 0.036, and originally the mission said that it needs to be less than 0.04, so we are in our requirement. So that's the whole process, and it has been a lot of work to get all these people working on these sites and getting provided data to SNAP, and especially early in the mission, the data needed to come in fashion, so we need to process it fastly, quality check fast, and get these comparisons going really fast. So it's speed of work, but SNAP was the first mission that really measurements also in addition to more in situ ground observations to have like higher resolution remote sensing measurements and so forth. So we are now working on improving the SMAP soil moisture over forested sites. Forests are super important for multiple reasons, for Earth's system and people's activities and people's resources. So that's why we want to understand that. At the moment, we are not providing validated soil moisture over forests. So you would go and open SMAP soil moisture product over forested, you would see soil moisture, but we are not making any claims how well that performs. So these green areas are the areas where we are flagging it as uncertain, the certainty estimate, uncertainty estimation, and these correspond to forests as you see. So it's because of we estimate the density of vegetation is over the threshold that we've traditionally been able to reliably measure soil moisture or retrieve soil moisture. So a little bit about that retrieval. This is, goes back to what Rashad was. So we have here a forest. So we have this parameter called vegetation over depth, describing the density of the vegetation. So higher this optical depth, the denser the vegetation, harder it is to microwaves to penetrate through. And then we have the soil permittivity, which is the soil moisture, as Rashad explained. So we have these parameters here. And now we have this high layer of vegetation, and there are some additional parameters affecting the radiation. There is some scattering and the temperature, it emits temperature, which is also received by the radiometer. As Simon explained, its radiometers are receiving this passive energy from the ground and also from the vegetation. So we need to understand how the vegetation itself emits radiation in order to successful retrieval of these parameters. On the ground, there is the roughness of the soil. So there is permittivity of the soil, but then we need to understand how that permittivity translates into radiated energy through that interface of soil and air, which is affected by the geometry of the interface, and also then the temperature of the soil. So we need some additional parameters also, and then we get to the soil moisture. But we retrieve soil permittivity and derive the soil moisture from that, knowing some other additional soil composition parameters, how clay it is, or those kind of things. Additionally, there is then in the air-soil interface, there is easily in forested environments a lot of leaves and moss, lichen, all kinds of things depending on the type of forest. So these problems are the ones we are trying to solve with the Forest Fit campaign that we this Forest Fit campaign, which we executed at two main locations, so northeastern temperate forest in the US and then the southern boreal forest in Canada. So what we did over these sites was we deployed, these two examples show the pins here are the deployment of the stations within these locations here in northeastern US. So we have a multiple station in soil moisture, and it actually occurred over 40 years. So those were like core site measurement going on at these locations. But then in addition to that, we then ran intensive observations 2022, where we made a lot of additional measurements in order to understand better all these different components I was just talking about. So here is an example of deployment of the stations. You see, under the forest, these stations, they are getting, power through solar panel, and then run, there's air temperature. There's also some sensors which were deployed, which were experimental setup, and proved to be very useful for this kind of purpose because they measure how much water, they respond to the changes of water content in the trees, and that affects the pulp density collection. So we want also one of the soil areas to know the pulp density of soil, so we can, there are different ways of doing it. This is this fancy way of digging a hole, taking the soil and then filling it with water to get the volume. Here are the tree measurements, all kinds of tree measurements to measure their geometry. So we had a lot of people participating in this experiment, and they were making measurements at these locations. So not only the soil, but then the vegetation, like diameters of the trees and tree heights and their distributions. Here is an example of soil sample collection. So the actual physical sample of soil. It's a traditional way of measuring soil moisture. So I was showing a lot of pictures of probe measurements, but then here an additional way of doing it is actually collecting a sample of soil, weighing it, and then drying the sample and then weighing again, and then the lost weight is corresponds to how much there was water. So you get the accurate soil moisture estimate of soil which they are collecting here. We want to also know soil, the vegetation water content, so we can branches, sample the branches, dry them the same way, and get the water content of tree branches and leaves, which is the leaf sampling. So they cut down the sample of leaves, and then we take the photograph for area, measure how much there was area in those leaves, and then we measure the rate of them, determine the water. Did huge effort, so roughness was here measured in this example of a couple of ways of doing that. Here, the first top row shows this board measurement where you have these pins that profile basically the shape, and then you take a photograph of those pin positions and get the soil profile. And at the bottom is a iPad LiDAR measurement of the soil, which is a little bit tricky to process, but in principle, that kind of just everyday iPad or iPhone LiDAR can be used to characterize the roughness. So, but then there are other ways of doing these same measurements. So characterizing the tree geometry, we can use this more powerful LiDAR, this portable LiDAR that was City College of New York deployed at these measurement locations, and you get this 3D representation of the forests. Very neat way of getting the exact measurement location, exact locations of the trees, and height of their branches and different estimations. It requires a lot of processing too, of course. Nothing is ideal, and there's this point cloud has basically noise and interfering factors that need to be resolved in order to get these actual parameters that can be used. But there is, it proved to be a very, very useful way of characterizing those bigger forest areas. And another very interesting way of measuring the effect of vegetation is this. So Simon and Rosal were talking about the GNS reflectometry, but then you can also use reflectometry in different, so you can have two receivers, one measuring it in open area, and the other one under the forest canopy, and then you compare how much the radiation you receive from those GPS satellites, and then you get the one that is under the canopy has the attenuation corresponding to the vegetation characteristics. And so there was a group from University of Georgia who deployed this receiver under the canopy. They either walked around it with this helmet. They actually deployed this Boston Dynamics robot dog, and it through the forest and while measuring its radiation, which was a very futuristic thing to see. So there are some examples of those measurements. Mr. doesn't tell you much, but they did those measurements in many areas, and you get those different signals that are shown here, but they don't actually tell you much. Okay, so these are huge efforts, and one of the things I really want to emphasize, there's a lot of people involved, and after the experiment, we had two workshops where we discussed about all these findings from these measurements, and how the processing is going and all that, but also then what we've learned and what eventually what we can do better in the future, and then we've learned a lot, and there is all
But this is really the bottom of how the satellite data is made and then validated. And thanks again for all the presentation. We have one more presentation from Dr. Jonghan Park. He will give a final presentation, and then we have opened the floor for questions and comments and so on like that.
안녕하세요. 저는 편하게 한국말을 하겠습니다. 저는 정한이라고 하고요. 지금 먼저 해주신 교수님께 감사 말씀드리고요. 저는 이제 나사 고다드 스페이스 프라이센터에서 그중에서 하이드롤로지컬 사이언스 랩에서 일하고 있는 정한이라고 합니다. 여기 안에 계신 발표해주신 닥터 민주시 박사님과 같이 있고요. 먼저 이렇게 많은 분들 앞에서 발표를 오래 했는데 좀 이렇게 긴장되고 하네요. 근데 이제 발표할 수 있는 기회를 지식대로 환경공학부와 이제 김영록 교수님이 좋은 기회를 주셔서 이렇게 여러분 앞에 이렇게 소개를 해드릴 수 좋은 기회가 된 것 같습니다. 그래서 저는 이제 뭐 앞에서 많은 분들이 이제 소유물질에 관해서 뭐 테크닉이나 유튜브나 뭐 캘가리 사이트에서 많이 했는데 저는 좀 더 나사에 제가 이제 한국으로서 나사를 일하는 것 때문에 좀 나사에 대한 설명, 소개와 그리고 제가 하는 일 관련 앞으로 좀 이렇게 박사나 석사 지금 대학원생들이 많이 계신 걸로 아는데 앞으로 만약에 미국에서 어떤 리서치 커리어를 할 수 있을지 어떻게 하면 할 수 있는지 이런 것들을 간략히 소개하는 그런 시간을 갖도록 하는 것 같습니다. 그래서 이제 먼저 소개를 한번 먼저 드릴게요. 저는 이제 학부는 이제 전기전 연대전공학부 나오고 이제 석사를 카이스트에서 했고요. 그 이후 유학을 나가서 월스테이트 전기 전자공학부 일렉트리컬 엔지니어링 박사를 받았습니다. 노아 미국 기상청 해양대기청에서 연수 근무를 하다가 2002년은 지금 미국 나사 고다드 스페이스 프라이센터에서 근무를 하고 있습니다. 먼저 이제 나사라고 하시면 많은 분들이 이제 알고 계실 것 같은데요. 먼저 이제 심벌 아래쪽에 있는 심벌 많이 보셨잖아요. 그게 예전부터 사용한 심벌인데 몇십 년 전에 좀 더 모던한 이런 이미지를 갖고자 위에 있는 빨간색 심벌도 사용했다고 해요. 한 15년 정도 사용했다가 지금 했다고 하는데 두 가지 심벌을 이제 적절히 조화하면서 아직 사용되고 있는 상황. 지금 미국에 다양한 나사 센터들이 있어요. 그래서 10몇 개 정도가 존재하고 다양한 센터들이 존재하고 있습니다. 그 중에서 좀 대표적인 것 소개해드릴게요. 그래서 보통 많이 여러분들이 알고 계시는 이제 케네디 스페이스가 이제 플로리다 올랜도에 있는데요. 보통 이 로켓을 쏘는 장소를 많이 알고 있죠. 그래서 옆에 보이는 경납 같은 데서 로켓을 조립하고 만들어서 이제 위에 보시는 이제 런치한 발사장으로 사서 이제 발사를 합니다. 저런 발사장이 꽤 많이 있는 걸로 알고 있고요. 또한 그 근처에서 스페이스 산업이 이제 발전됐기 때문에 스페이스 관련 박물관이라든지 이런 전시하는 공간 아이들이랑 함께할 수 있는 좋은 뮤지엄도 있습니다. 그 다음으로 많이 알고 있는 게 휴스턴의 텍사스 휴스턴에 있는 존슨 스페이스 센터인데요. 가보진 않았지만 저렇게 생겼다고 해요. 많은 건물들이 있고 보통 스페이스 관련 연구라든지 아니면은 위성과 아니면은 ISS라든지 우주에 있는 분들과 이제 통신을 하는 사망실 중계실 이런 게 있다고 해서 많이 있고요. 여기서도 미국에서 되게 큰 규모의 뮤지엄도 존재하고 있어서 많은 분들이 찾고 오곤 합니다. 이거 말고 이제 저희는 얼사이언스나 연구를 하기 때문에 연구 목적으로 보면 아까 많은 연구소가 있긴 했지만 보통 이제 동부와 서부를 대표하는 연구소가 두 개가 있어요. 그래서 서부에는 이제 제트 프로펄션 랩이라고 해서 캘리포니아에 있고요. 동부는 이제 고다드 스페이스 플레이스 센터가 있습니다. 그래서 보통 JPL이라고 많이 부르는 그 연구소는 캘리포니아 로스앤젤레스 북쪽에 있는 페사디나라는 근처에 존재하고 있어요. 그래서 뒤에 있는 벨리 많이 있고요. 벨리 아래 이렇게 많은 건물들이 위치해 있고요. 제가 속해 있는 인더 스페이스 플라이 센터는 짧게 말해서 GSFC라고 부르는데 워싱턴 DC 살짝 북쪽에 있는 메릴랜드 주에 그린벨트라는 곳에 존재하고 있습니다. 그래서 빌딩들이 한 30몇 개 정도 있는 걸로 알고 있습니다. 그래서 다양한 연구들이 나사에서 서쪽과 이제 동쪽에서 이렇게 이루어지는 현상이 되고 있습니다. 어떻게 보면은 다양한 연구를 하고 있지만 어떻게 보면 좀 경쟁하는 구도기도 해요. 그리고 이제 제가 있는 이제 고다드 스페이스 센터에 작년 봄이었죠. 대통령님께서 이제 워싱턴 DC 하시는 계기가 있었는데 그때 처음으로 이제 저희 센터에 방문해 주셨습니다. 그래서 부통령이신 해리스 부통령의 안내를 받으면서 고다드의 곳곳을 좀 살펴보셨고요. 그리고 이제 고다드 스페이스 플라이 센터에 또 한국 분들이 많이 계세요. 한 4, 50분 정도 국내에서 박사하시고 나오신 분들 많으셔서 통틀어서 한 4, 50분 정도 계십니다. 오른쪽에는 사진 그때 그 당시 대통령이 오셨을 때 한국 분들 모셔서 이렇게 간담회했던 사진이 있어서 한번 넣어봤습니다. 그리고 또 고다드 연구소에서 이제 많이 이제 관리하고 운영하는 것 중에 유명한 것이 제임스 우주 망원경이 있는데요. 많이들 들어보셨을 거예요. 그래서 이거는 이제 보통 예전에 상황이 있었는데 그게 노후화됐기 때문에 그걸 신식으로 좀 런치한 케이스가 허블 망원경의 지평보다 한 3배 이상이 크다고 합니다. 저도 자세히는 모르지만 그런 방식 저렇게 생겼다고 하고 지금 이제 런치된 상태에서 다양한 별과 은하 같은 우리가 모르는 미지의 우주의 그 다양한 사진들이 이렇게 지구로 전송되어 있다고 합니다. 봐도 매우 아름다운 걸 볼 수 있죠. 그리고 이제 혹시 많은 분들이 보셨겠지만 이런 제임스 웹이 우주망원경이 굉장히 유명하기 때문에 국내에서도 많은 관심을 가졌고 이쪽에서 이제 우주에 실질적으로 연구에 참여하신 한국 분이 계세요. 손상만 선생님 계셔서 이런지 다른 방송들도 많이 나와서 접하신 분도 계실 거라고 보고 있고요. 혹시 접하시지 않으신 분들 한번 찾아서 한번 보시면은 되게 재미있게 보실 수 있을 겁니다. 보통 제가 이제 나사에서 일한다 하면은 사람들이 많이 물어봐요. 외계인은 있냐, UFO가 있냐, 다양한 우주에 관련된 걸 많이 물어보는데요. 보통 이제 나사에서는 여러분들이 잘 아시겠지만 얼사이언스 분야도 이제 존재합니다. 얼사이언스 나사는 뭘 하냐면 지구를 관측하고 측정하고 분석하는 그런 역할을 하고 있습니다. 그래서 보통 지구를 크게 3부류로 나누면 이제 대기 부분, 그리고 지 표면 부분, 그리고 지구 아랫부분 이렇게 3부분 나눠서 좀 구분을 해서 연구를 하고 있는 시점이고요. 지금 그리고 다양한 국내 세계에서만 다양한 기후 변화라든지 재해라는 게 많이 발생되고 있지 않습니까? 그래서 나사에서도 이런 거에 대해 관심을 갖고 좀 보고 있어요. 그래서 그중 하나가 이제 가뭄인데요. 가뭄은 이제 계속 캘리포니아라든지 우리나라 마찬가지고 많이 가뭄이 일어난다 해서 많이 관심을 갖고 있고요. 또한 그 다음 이제 이벤트 홍수도 이제 많이 났기 때문에 많이 그런 2023년에 캘리포니아에서도 이렇게 심한 홍수가 나서 관심을 갖게 되고 있습니다. 또한 다른 마지막 하나는요. 산불인데요. 산불도 마찬가지로 작년에 하와이에서 되게 크게 일어났고요. 매년 캘리포니아 밸리에서 산불이 일어나기 때문에 이러한 기후 재해 아니면은 기후 환경 변화에 대해서도 나사 그런 영향을 인지하고 그쪽으로 관련돼서 많은 연구를 집중하고 있습니다. 그래서 저희 이제 이런 얼사이언스 어플리케이션에서 고다드 스페이스 프라이스 센터에서는 610이라는 코드네임으로 이제 얼사이언스 디비전이 있는데요. 그 얼사이언스 디비전 안에 다양한 분야의 연구소들이 존재합니다. 그래서 글씨가 잘 보이는지 모르겠지만 위에 보면 대기 쪽 관련, 그리고 이제 프라이스피어 극지방 연구하는 연구소, 오션, 그리고 하이드로로지컬 한 부분, 지오데시, 바이오스피릿 여러 가지가 있고요. 저는 그 중에서 이제 617이라는 하이드로로지컬 사이언스 랩에 속해 있고요. 저희 이제 올사이언스 디비전이 보통 저희 고다드 스페이스 아까 말한 30몇 개 빌딩 중에서 빌딩 33번에 위치하고 있고 빌딩은 저는 왼쪽에 보시는 그런 빌딩에서 일을 많이 하고 있습니다. 앞에서도 님이 보여준 그림하고 비슷한데요. 이런 다양한 얼사이언스 어플리케이션을 하기 위해서 나사에서는 다양한 위성을 지금까지 쏘아 올리고 있고 앞으로도 계획 중에 있습니다. 그래서 이 그래프에서는 1900 중반부터 지금까지 그리고 앞으로 런치될 그런 위성 미션들에 대해서 설명해놨고요. 보시면 아까 많이 설명했던 스맵, 시그니스, 아니면 센티넬 이런 것도 있고요. 앞으로 런치될 미션 중에서는 나이사 미션 같은 미션. 그래서 제가 앞에서도 말씀드렸지만 제가 하는 분야가 나이사 미션에 대한 소일 물질을 좀 하기 때문에 이쪽에서 설명을 한번 드리겠습니다. 나이사는 이제 나사와 인도의 나사 같은 우주청이죠. 거기서 이제 합동 쌓은 미션을 하는 거고요. L밴드와 S밴드를 결합한 수입사 미션으로 런다 2025년 6월 8일로 예정되어 있습니다. 그래서 보통 210km의 수와 3에서 10m 정도의 very 파인한 스페셜 레졸루션을 가지고 있고요. 같은 원리이기 때문에 12일 정도의 이비젝트한 리비젝트 타입을 갖는 특색을 가지고 있습니다. 보시다시피 월사이언스, 이코시스템, 파라스피어, 소리더스 다양한 리모트 센싱 어플리케이션을 위해서 인터필이나 백스캐터 메저먼트까지 될 예정입니다. 그 중에서 소일 물질 관련돼서는 저희는 이제 나이사 미션에서도 소일 물질 프로덕트를 개발하고 퍼블릭에 공개할 예정인데 이 데이터는 200m 베이스로 만들어질 예정이고요. 이는 이제 필드 스케일 베이스로 해서 미국에 있는 필드들이 보통 200m 스케일 기준으로 많이 해서 그런 200m 메트릭스 볼 정제고요. 이 프로덕트 안에 소일 멀치 알고리즘이 세 가지가 있어요. 그 중에서도 체인지 디텍션 메소드를 기반한 저희의 타임 시리즈 레이쇼 알고리즘이 제가 이제 일하고 있는 거 여기 이제 이 프로덕트 안에 들어가서 좀 더 설명을 드리겠습니다. 아까 리트리버 박사님께서도 말씀해 주셨지만 백스캐터링을 모델링하는 방법은 세 가지 텀의 합으로 보통 기본적으로 모델링 많이 해요. 그래서 서피스에 관한 컨트리뷰션 텀, 그리고 서피스와 베지테이션의 인터랙션 텀, 그리고 아니면 볼륨 스캐터링 텀을 나누는데 보통 여기서 이제 같은 엘밴드이기 때문에 볼륨 스캐터링 텀은 매우 작다고 가정을 해요. 그렇기 때문에 저희는 첫 번째 텀만을 많이 고려를 하고요. 좀 쉽게 말해서 그냥 퍼스트 텀이 되긴 한데 이거를 스캐터링, 퍼스트 오더 스캐터링 모델로 어프로크시메이션 한다면 이 텀은 어떤 알파라는 펑션과 러프니스 펑션의 곱으로 표현할 수가 있어요. 이 알파라는 함수가 있는데 알파가 뭐냐면은 어떤 다이렉트 컨트리인 엡실론과 인스턴스 앵글의 지오메트리에 관한 펑션인데요. A의 경우 같은 경우는 프리시너스 코에피션트 동일한 형태로 나타나게 됩니다. 그래서 이게 알고리즘의 네임이 타임 시리즈 레이쇼 알고리즘이기 때문에 어떤 타임 시리즈 메저먼트가 있다면 그 타임 시리즈 메저먼트의 레이쇼를 구해서 그거를 이용하게 됩니다. 아까 말씀드렸다시피 요 시그마 낫이 어떤 알파 텀과 러프니스 어게스테이션 텀의 곱으로 나눠지게 되는데 그걸 이제 레이쇼를 나누게 되면은 보통 같은 오rbit을 놓기 때문에 러프니스 텀은 캔슬아웃 한다고 가정을 하고요. 그리고 베지테이션 텀 같은 경우는 짧은 기간 베지테이션의 영향은 좀 미미하다라고 가정을 하고 접근하기 때문에 또 이거는 알파의 알파 펑션의 B로 분석할 수 있다. 이런 성질을 이용해서 저희가 리트리버를 하고 있습니다. 알파라는 사용하기 때문에 알파 어프로크시메이션 메소드라고 불리고요. 이제 같은 경우는 세 개의 타임 시리즈 메저먼트를 사용합니다. 그래서 세 개의 메저먼트를 사용하는데 그거를 이제 레이쇼를 취하기 때문에 보통 식이 두 개고 변수가 세 개인 저런 매트릭스 이퀘이션을 우리가 구하게 됩니다. 근데 두 개고 이제 변수가 세 개이기 때문에 어떻게 보면 풀지 못하죠. 언더스탠드 프로그램 때 이걸 풀기 위해서 어떤 어디셔널 인포메이션이 필요하게 되는데 그걸 위해서 저희는 스맵 레디오미터의 파라메트라직 데이터를 사용하면서 그 값을 이용해서 알파의 미니멈과 맥시멈 값을 폴싱에 기준으로 해서 리니어 리스트 스퀘어 프로그램을 풀게 됩니다. 이제 알파를 구하게 되면 아까 정의했던 수식에 의해서 인버스를 엡실론을 구하고 다시 다이렉트 리스트 모델을 통해서 소일 물질 값을 구하는 게 기본적인 개념이 되겠습니다. 이제 전반적으로 이제 이 알고리즘은 다른 복잡한 포워드 스캐터링 모델이 들어가지 않았기 때문에 매우 간단하다는 장점이 있고요. 또 그렇기 때문에 저희가 이제 글로벌 데이터 프로세싱을 하기 때문에 그러면서 좀 용이하지 않나 보고 있습니다. 또한 다른 어디셔널한 앤셀리 데이터가 많이 필요하지 않고 단지 소일 텍스처 인포메이션을 하기 때문에 좀 더 그런 점에서 장점을 잘 활용할 수 있고요. 만약에 단점이라면 아까 말씀드렸다시피 문제를 풀 수 없기 때문에 어떤 알파 펑션의 미니멈과 맥시멈 값을 폴싱해주기 때문에 거기에 대한 좀 단점이 있을 수 있고 또한 가정으로서 베지테이션의 변화가 미니멀하다고 가정했는데 그러지 않은 경우도 있기 때문에 그런 경우에 좀 단점이라고 할 수 있지만 다양한 이런 경우에서도 잘 워킹한다라고 보여줬고 다양한 미션 데이터에 레이더 데이터에 좀 했을 때 잘 작동함을 볼 수 있어서 저희는 이 방식을 사용하고 있습니다. 그래서 이런 알고리즘을 이제 개발을 했고 이제 평가를 해야 되는데 보통 이제 아직 런치하기 전이기 때문에 프리런치 어널리시스로서 레이더 메저먼트를 사용했습니다. 이유는 같은 엘밴드를 사용하고 있고 또한 이제 컴퓨테이션이 비슷하기 때문에 그런 스맵 레이더 메저먼트를 나이사 소일 물질을 위한 타임 시리즈 레이쇼 알고리즘을 세팅하게 썼고요. 여기 보시면 오른쪽에 보시는 동영상의 위쪽이 저희가 한 리트리브를 있고 아래는 그거에 해당하는 스맵 레디오미터 데이터를 같이 이렇게 보여드립니다. 보시면 알겠지만 어떻게 보면 스페셜 패턴을 보기 위해 이렇게 표현을 한 건데 보통 보시면 되게 비슷한 걸 알 수 있고요. 예를 들어서 사우스 아메리카 정도 아마존 같은 경우는 되게 웨트한 특성 그리고 아프리카나 오스트레일리아 같은 경우는 좀 더 드라이한 특성을 보여줄 수 있어서 비슷하다. 그리고 또한 코렐레이션 콜리션을 봤을 때 0.9라는 값이 나오기 때문에 굉장히 근사한 값을 가진다 이렇게 볼 수 있습니다. 하지만 이런 것들은 이제 스페셜 패턴을 보기 아니고 정확한 어세스먼트를 하기 위해서는 리셋춤의 측정값을 사용해야 되는데요. 앞에 전에 안드레아스 박사님께서 설명해 주셨지만 저희는 이제 13개의 스맵 폴 밸리데이션 사이트를 먼저 이용했습니다. 이 폴 사이트가 전 세계 다 있고요. 미국, 캐나다, 스페인, 또한 만약에 이제 좀 더 이제 논크롭 사이트만 보를 했을 때는 이거보다 좀 더 좋은 걸 보이는 걸 알 수 있습니다. 그리고 또한 뭐 이뿐만 아니라 미국에는 한 US 폴스 그라운드 소울머지 네트워크가 존재합니다. 수백 개의 USD에서 관여하는 스캔 네트워크 그리고 노아에서 하는 USCR 네트워크가 많이 있고요. 요것들이 여기서 비슷한 어세스먼트 어나리시스를 할 수 있습니다. 제가 한 건 이 정도고요. 이제 뭐 다른 분들 많이 이제 리서치를 하시는 대학원생들 많이 계실 텐데요. 이런 분들이 이제 앞으로 어떻게 혹시 만약에 미국에 오시거나 이런 생각이 있으신 분들 어떻게 접근하면 좋은 거냐 아니면은 어떤 오퍼튜니티가 있는지 제가 한번 간략하게 정리해봤어요. 그래서 만약에 이제 대학원을 졸업하시고 미국 온다면 다양한 연구 기회가 대학교에도 있을 수가 있고요. 보통 이제 정부나 대학 산하의 리서치 인스티튜트가 많이 있어요. 그래서 유카, 에카 아니면 다양한 MIT 링컨이라든지 다양한 랩에서 되게 운영하고 있는 좀 얼사이언스 특성 랩터 그런 랩들이 좀 더 관심 있게 보시면 되고요. 또한 저가 있는 것처럼 US 사운드 에이전시에서도 많은 이런 기회를 제공합니다. 나사 노아도 있고요. 미국 국민무예대학 유니스티 그리고 표준 쪽 관련할 수 있는 리스트 같은 또 많은 오퍼튜니티가 있는 걸 쓰고 있습니다. 또한 여기가 지금 환경 에너지 공학부잖아요. 에너지나 테크놀로지 관련해서 미국에서는 이제 연구를 위한 내셔널 랩이라는 게 존재해요. 그래서 패시픽 노스웨스트 아니면 노스아즈노스 아니면 샌디아 이런 다양한 내셔널 랩들이 있기 때문에 많은 기회가 있다고 보실 수 있습니다. 하지만 이게 자기 잘 보잖아요. 보통 이제 설치를 많이 하시는데요. 보통 구글이나 링크드인 같은 거 많이 사용하시는 것 같고요. 또한 미국에서는 좀 잡사이트를 좀 스페시픽하게 할 수 있는 사이트가 이제 인디드 이런 게 있어서 많이들 보고 지원을 하는 추세입니다. 하지만 제가 볼 때는 조금 이게 대학원생에 공부하신 분들에 있어서는 미국은 조금 레퍼런스와 좀 크레딧이 중요한 세상이에요. 크레딧이 신용 그리고 레퍼런스는 추천이 이런 제도인데 그렇기 때문에 뭔가 이 모든 사람을 하이어하기보다는 좀 뭔가 관계를 형성한 사람을 뽑는 경향이 있어요. 그렇기 때문에 뭔가 자기가 미국에서 관심이 있는 연구자님과 좀 뭔가 커넥션이 있거나 아니면 자기 지도 교수님께서 많은 영향력이 있는 사람이 있다면 그게 더 제일 최선이고 만약 그런 게 없다면은 뭔가 이제 그런 관계를 위해서 컨퍼런스에서 자기를 어필하는지 아니면 자기 연구 결과를 좀 더 이메일을 만나서 좀 이렇게 공유할 수 있는 그런 기회가 있으면 더 좋을 것 같습니다. 그리고 나사에서는 또 이런 직접적인 나사 포스트 닥터 프로그램이라는 게 존재해요. MPP라고 많이 부르는데요. 이 제도에 대해서 소개를 해드리려 합니다. 그래서 MPP라는 건 보통 1년에 3번 정도를 합니다. 3월, 7월, 11월. 그리고 이제 여기서 써 있는 건 US 시민권이라든지 필요하다 하지만 제가 알기로는 포렌 내셔널, 그러니까 외국인에 오픈된 프로그램입니다. 그렇기 때문에 많이 제가 봤을 때 많은 분이지만 그래도 여기 선정된 분들이 계시고요. 만약에 선정이 된다면 미국에서 생활할 수 있는 스타이펜드, 그러니까 생활비라든지 다양한 베네핏 제공이 되고요. 또한 한 번 선택이 되면 3년 정도 지속될 수 있는 펀드가 제공된다고 합니다. 근데 이런 MPP를 지원하기 위해서 어떻게 해야 하느냐? 보통 아까 말한 그 3개의 데드라인이 있지 않습니까? 그때 이제 오퍼튜니티가 웹사이트에 검색, 그래서 그 오퍼튜니티를 검색한 다음에 거기서 이제 자기에 관련된 연구와 센터 그리고 그런 거를 이제 설치를 한 다음에 만약에 내가 맞는 연구 오퍼튜니티가 있다 하면 그 오퍼튜니티를 관할하는 연구자 PI에게 연락을 해서 내가 이런 연구에 관심이 있다 말을 하면은 이제 어떤 쪽으로 이렇게 자기가 관심이 있고 이런 쪽으로 프로포저를 썼으면 좋겠다 이렇게 말할 거예요. 왜냐면 이 프로그램을 서밋하기 위해서는 이제 MPP 프로그램을 작성을 해야 되거든요. 그래서 15 정도 페이지에 대해 나의 연구 관심 분야, 앞으로 일을 할 거냐 이런 것들을 써서 서밋을 하게 됩니다. 그리고 이제 한 서밋을 하고 나서 3개월 정도 있으면 이제 결과가 나오는 그런 MPP 프로그램. 그래서 이 정도로 제 발표인데요. 근데 이제 제가 말씀드릴 거는 제가 이제 지스테 온다고 해서 한번 검색을 해봤어요. 김영석 교수님도 계시고 해서 검색했는데 보니까 되게 이런 에너지 환경 분야에 되게 많은 교수님도 계시고 다른 학교에 비해서 좀 더 많은 교수님이 계시고 좀 뭔가 특성화됐다는 느낌이 많이 있어요. 그래서 제가 볼 때는 만약에 이런 얼사이언스라든지 아니면 위성이라든지 이런 연구에 좀 관심이 있다 하시면은 만약에 전공을 정하지 않으신 1학년 학부생분들이나 아니면 대학원 진학을 좀 고려 계시는 학부 9년차 학생분들이 계시다면은 제가 볼 때는 환경 에너지 공학부도 하나의 선택이 될 수 있다는 말씀을 지금 한번 마무리를 하고 싶고요. 만약에 혹시 지금 이제 이제 질문 시간을 갖긴 가질 텐데 혹시 추가적인 질문 있으면 혹시 얘기해 주시면 제가 가능한 한도 내에서 답변해 보겠습니다. 감사합니다.
So from now we are going to answer some questions that we previously received by the so could you go? I think I got around like 30 questions, but you know because we have the time limits, we cannot answer everything. So there is a like we have 6 questions, I guess. So maybe Simon, you can start question 1 if you like. The question is, given the current limitation in satellite resolution and temporal frequency, how does the SMAP mission ensure accurate soil moisture measurement in regions with rapid land use change or where ground validation data is? That's a great question.
This is a very good question. I think it's a billion-dollar question. And so I don't really know the answer about how to address this. And I think the question is really probably for everybody to address. And so there are many elements, right? So the world changing, landscape changing. And then Roger has mentioned to you about this ideas, right? Satellite retrieval algorithm, which we don't include the possibility of changing landscape. Roger indicated that we need to bring a lot of ancillary information, right, to calibrate this set brightness, right, radiance into the soil moisture. Right, the landscape changing, that parameter change. So how do we address that? And so there are many power approaches. I'm not saying that I will address the issue, and so I think we all recognize, right, there are many different approaches. Radiometry, radar, reflectometry, they all see the world from different angles. So maybe that's a way. So maybe once you bring the information, right, from multiple setup with a different technology, ideally, right, mathematically, if you get more independent measurement, you can infer more information. So maybe that's a way. So then in the future, when you combine the data from multiple setups together, now you can actually investigate more than just the soil moisture. But you can use the data from all 3 different types of measurement technology to infer more than just the soil moisture of the landscape. And then there's another satellite which we did not really cover, but and Jung has already given a big picture to you. There are many other satellites that provide the measurement at something high frequency, not a microwave, right? Frequency. They see the world in a different view. So maybe all those need to come together. And I think that's a foundation probably NASA has been building upon. And then once you get the information together, maybe there's a grand solution to address this question. Okay, so I'm not going to give you an answer, but maybe that's a possibility that you guys can all do. So what does this mean? There are many PhD theses you can work on.
Thank you, Simon. And a related question, then we should go on. The second question is, with SNAP data being integral to understanding the water carbon energy cycle, how do you envision its application in the future, especially with the potential integration of AI and machine learning for precise climate modeling and prediction? Rajat?
I think you guys are more suited to do AI and machine learning than I am, but I'll try to give my perspective. You probably have a much better idea of doing that. I think we are in an era of large data volume being available to the world for change, research, or just earth science in general. Like for example, currently we are downloading, few terabytes of data, but when NISAR gets launched next year, NISAR data in 1 year is going to produce the same amount of data that NASA has produced in 50 years. So it is terabytes of data and processing that and trying to find the linkages between water cycle, energy cycle, carbon cycle, and you bring in SMAP observations, ISA observations with future, VIS-IR observations or IR observations, and atmospheric observations, and observations about the atmospheric chemistry, atmospheric pollution, PM 2.5, those type of observations. Then you can really understand the impact of the carbon cycle linkage with the water cycle linkage to the climate change. And that would be an opportunity for you guys in the future to do that connection using machine learning and AI.
That's a great answer. Thank you. Any more questions related to AI measurement competition? No? Okay, thank you. Let's move on to the third question. There must be someone who asked the question, but yes. Okay. Okay. And the third question is to observe soil moisture. It is important to investigate not only the moisture on the surface, but also the moisture around. How is the observation of underground moisture conducted? Can this also be by satellite? Into Greece, maybe. Simon?
Okay, this again is a very, very good question. So it's more the three-dimensional space, right, that we need to look into. So I think as Roger and Andre and John has all mentioned, right, the SMAP frequency is small, and so LN frequency, the wavelength is about that long. So it can get into the soil by about this much depth. But we all know, right, there's a lot of water further underground, right? So this question kind of asks, what kind of information, how we can infer that kind of information from something that's further below the surface that SMAP is small, the current set technology can provide. And so I think I mentioned earlier to you the lower frequency, even lower frequency satellite, like the upcoming ESA biomass mission, P-band, the wavelength is long, about a meter. SMAP wavelength is long. So the biomass band SAR mission can actually provide the data much deeper depths. And so that's a way, I think that's a direct way probably to provide further information on below the surface. So I think the data will be available, will be coming up. P-band biomass data is not ideal still, because the limitation of the swath width. So they have to use the dripping orbit. So when you come back to the same location in space, you'll be kind of about a month over the same location. So the repeat interval is really long. And so what does it mean? We know that the underground soil moisture changes slowly, right? Slower than the surface soil moisture. So maybe that data is useful, but it's not ideal. So what does this mean? I think the data can be explored, but then the further instrumentation, right, improvement in the future is needed. And so I was strongly encouraged, right, from both perspectives. There are engineering improvement we still need to work on. I think the many students here, you can think about that. From the engineering point of view, instrumentation is needed, better instrumentation needed. But from the science point of view, even with the P-band biomass data, which is not ideal, but maybe if you combine that with the machine learning or other more clever approach, maybe you can infer some information combined together with the high frequency data from the SMOS. That will allow you to actually figure out a more bigger time series type of changes that you can see underground. So I think that this is kind of the question. And then Andrea, maybe you want to talk about how the lower surface, right, so much can be validated from your perspective.
one thing, a completely different observation measurement is the gravimetric brace measurement, which is you measure the changes in the gravitation of Earth. So you get this total water change in the whole, like groundwater changes and everything combined into one when you detect these small changes in the gravitation field of the Earth that's being done. It's also super cautious, of course, on the radiometer, but you get another perspective of the soils, the water evolution when you combine that into all this. So that would just be what I would add on what Simon said.
Right, great. Thank you for it, sir. And any related question to Andrew, sir? No? Okay, let's move on. The first question is, when observing surface moisture through satellites, it seems that the observation data will vary significantly depending on the weather, and how do you take this into consideration when obtaining the data? Someone? Richard?
So this is a very interesting question. I would try to frame it a little bit differently. This also tells you the value of why you want really, really long-term data sets. We are in an era where we know there is a climate change happening, and we don't know what the impact of that is on the water cycle. The water cycle accelerating. You hear more and more about bigger hurricanes coming. You hear more about bigger floods, bigger droughts. If we don't have the data, we can't study that. And that's the reason why we need long-term records of water cycle, carbon cycle, and all those different cycles to be able to study what the impact of climate change is on the water cycle. Are the droughts more severe? Are the floods more severe? And that exactly is basically impacts the weather. We also have to make sure our retrieval algorithms are consistent with the future changes that are occurring. So we have to make sure we are not incorporating biases that we may not be able to study climate change. But the value of this data, climate change, is very critical because we don't understand what the implications of the climate change are to the water cycle. Is there going to be enough water for us for agriculture, for example? If there are going to be bigger droughts and bigger floods, I don't know. Unless we have that type of data, we don't have this.
This is fantastic answer. I didn't know that we need data for such stuff. And do we have one more?
So I just wanted to add the short time scale. So currently we measure with the SNAP, for example, on equator every 3 days soil moisture. But it has been identified that one of the most important things to improve in the future would be to increase that frequency even more, like get to the daily or sub-daily measurements of soil moisture to update the soil moisture estimates because of these weather changes which affect all the dynamics of the energy, water coupling on the surface and so forth. So while the improvement of spatial resolution is one very important thing for this future project, the other one is the increasing the observation frequency from the current is already every 3 days, but even better.
Any question to Andrew's answer? Okay. Do we have a few more questions? Let me see. It's kind of hard question, so maybe this is the last question, so let me do it. So if the Earth is the target for exploration, is it really necessary to use satellite to measure soil moisture? Of course, there is an advantage of easily covering large areas, but there must also be clear drawbacks, such as not being able to observe area obscured by cloud, and I believe the cloud may be larger error to the atmospheric transparency and other factors. I'm curious if there are any plans to extend such project to other planets, not just Earth. Any people from outside have to call.
The first part of the question, right? If Earth is the target for exploration. So yes, the Earth is the target for exploration. And so we all know, right, very clearly what we want to do that, right? We want to know the Earth a little bit better, right? How much do we know the Earth today? Do you know? How much do I know? Not too much, right? I don't have that much knowledge. How can we predict the climate change? How can we forecast weather change? We cannot. So yes, the Earth is target for exploration. And it is really necessary to the center. We all, the people here today, including myself, I think many of you are too, we all have a lot of experience in a few campaigns. Andre have put up a lot of big picture, right? Nice picture. Walking to the forest canopy. How many of you have done that before? Can you really walk into the forest canopy and make a management? Can you really do that? Have you tried it? Can you really walk into the forest with a very close spacing, with a tree, grass on the floor or on the ground? Can you do it? You probably say you don't want to do that, right? Because you don't know what's on the ground or kind of animal, snake, whatever that could be there. And so it's very difficult to get into. There are a lot of terrain and that's impossible to reach. And think about that on the top of the high mountain Asia, the Tibetan terrain. How many people can get up there? Right? How many people can actually walk up there? So the location on Earth is not reachable. So say that anyway. You gotta convince, right? So tell me what your answer is. Covering large area, yeah. So the small satellite, right? The source coverage. When it fly over, it can cover about 1,000 kilometer wide region. 1,000 kilometer. What does 1,000 kilometer mean? How wide is the South Pole? Anybody know the answer? The width? Right. So snake come over, easily cover the entire South Korea. Easily, right? One shot. So how fast was this flying in space? About 7 kilometers per second. In 1 second, it fly over 7 kilometers. So what's the South Korea? How many? 1,000 kilometers. So how many seconds would it take for a satellite to cover? 1,000 divided by 7, right? How many seconds? Right, you know the answer, right? So very quick. So if I give you a probe, like Andre showed you, you go out there, do the sampling, how much time will it take for you to cover the entire South Korea? Is it even possible? Right? Is it even possible? Think about that. So I don't think in practice, right, satellite is the only way that can cover the entire world, right? In the systematic approach, right? In the systematic time sampling point of view. So there's no other better way. And then the cloud project can cover that.
Let me ask you a question. You guys know about weather in South Korea better than I do. I'm not very familiar with it. What's the biggest impact of weather on South Korea? What drives the weather in South Korea? One person. Somebody. So, for example, there could be phenomena occurring over Tibet, or there could be something happening over in Mongolia area that impacts the weather in, Korea. Or there could be something going on in Russia that impacts the weather in Korea. By that I mean, there may be a drought or heat wave or something going on in those parts, or big snow event or some weather front. If you don't have a satellite, and if those countries don't tell you what's going on over there, you cannot predict what the weather is going to be in South Korea tomorrow. And that's where satellites come into picture, is they provide you a picture, irrespective of whether you have access to that part of the world or not, and they are there as your eyes. So with regard to the cloud, I mentioned earlier, we are using microwave observations, which clouds, they're transparent. It doesn't, we can see right through the cloud. Wavelength is this long, right? Clouds are, molecules are very, very small. So the wave just goes through. It doesn't matter whether it is daytime or nighttime. You can see the same observations at 6 o'clock in the morning from SMAP and 6 o'clock at night from SMAP. So daytime, nighttime doesn't matter in microwave. That's one of the advantages. Whereas when you're using visible data, if it is dark, you cannot see. You only see lights. You can't see what they're, in terms of the NDVI, for example. And you cannot do it in the dark. You can only do it in the daytime. But microwave, it doesn't matter whether the day or night, whether it's cloudy or not cloudy. And the last one is probably the biggest challenge, the question you asked, whether are we plans to extend this project to other planets, not just Earth. I think different agencies are interested in knowing whether there is water on Mars, for example. And they are looking at spectrums and those type of things, whether to explore whether there is water on the dark side of the moon, for example, or on Mars. Unfortunately, I'm not an expert in that. And I don't intend interested more in our planet Earth, where we live on. We have to, at least in the kind of lifetime, I see us living over here, and what the impact of changes on our planet, and how do we address the water crisis or the food crisis on this current planet.
About the last question, right? Whether there's a kind of interest, right, to look into other planets. In fact, probably close about 10 years ago. So JPL produced a program for some Mars program. So JPL managed a Mars program for NASA, and so there was one day the director of the program called me, Simon, come to my office. And then he called another person. Tell me what you guys think, that director, tell me what you guys think about what can be done to explore maybe the ice, right? Consider so much, but the ice or whatever kind of under the surface. So what's the motivation? The motivation is, could there be enough water on Mars under the surface? Maybe water, maybe ice, right? That can be used to sustain the future, right? Generation of the inhabitants of the Mars who got on the Mars and they don't have enough water, right, from the Earth, right, can support them. Can we explore whatever liquid type of resource we are available? And so the other person who brainstormed is it would be maybe radar, right? NASA radar type of technology. The L-band radar can actually penetrate through the soil. Although earlier we say that we tell kind of, the L-band frequency can only penetrate that much. But remember, if you think about that, Mars is very dry. It's dry. So L-band frequency can really go really deep. And so we say, okay, maybe on frequency, maybe we can do something. We can send a radio signal through it. The signal bounce back. Maybe if you're smart enough, you can tell from the reflected signal whether there's ice or not. Okay, then we look further, right? Oh, so the water ice contact below the surface probably was spatial extent, right? Maybe even a vertical distribution. Maybe it's not uniform, right? Like not uniform, right? There's something like that. type R. And then there's another type of radar we did not talk about today. That's called ground penetration radar. You can penetrate through the ground. You can see beta delay of signal, and then that can actually tell you the vertical information. So maybe combining those radar technology, NASA, ESA has been developing many type of radar technology. You put them together, that will allow you to get a more 3D picture of the Mars. Maybe beyond the Mars. There's another 20 minutes, Europa. And if you are following story, NASA is going to launch a mission pretty soon, right? The hypothesis that there is a layer, right? Something below the icy surface of Europa. So the radar technology probably can do something about that. So maybe that's a method, right? Maybe it's a water, who knows, right? So does NASA, ESA have an interest? Yes, we do have interest. And if there's water, right, in any other planet, then I think everybody will be pretty excited because there's one implication. Water can create some life, right? Biology is very important. So NASA has the phone call biology, right? Not biology of planet, biology of planet. Yes, NASA has the planet idea, right? To the other planet. In terms of availability of water, available to possible of create life in the past. All right? Anybody? I don't want to add anything.
Thank you so much, Simon. Yeah, it's about time to conclude the seminar. If anyone has further questions, just please raise your hand. Doesn't need to be academic related, but anything scientist here. No more questions? Okay, then let's give a round of applause to the presenters. We will take a picture front of the Orion board now, so please go outside and take a picture together. And 그 전공 설명회 환경 에너지원 전공 설명회 지금 103호에서 하고 있거든요. 거기 지금 이렇게 맛있는 것도 주고 상품도 준다고 하니까